Okay, so we've started to introduce the idea of what we would call a Fourier transform, or sometimes called the frequency spectrum. Basically, what the Fourier transform tells us is if I have a signal, in general, what it tells me for any signal, subject to some constraints, but it doesn't necessarily have to be periodic, that tells me at what frequencies that signal has energy. Now, in the special case that I have a periodic function, which means that I know that it can be represented as a sum of complex exponentials, like so, then in that special case, for our periodic signal, what I have is a Fourier transform. Basically, this guy is a complex function, and this complex function tells me basically the frequencies at which my signal has energy. So because of the fact that this signal is made up of a sum of sines and cosines, the only frequencies at which I have energy are at those same frequencies where I have sines and cosines. Okay? And those sines and cosines are harmonically related, meaning that the frequencies are integer multiples of each other. Okay? And so that's basically what this summation is going to tell us. Now, at some level, it seems like this is maybe kind of a trivial step from the Fourier series, and it kind of is for a Fourier or for a periodic signal. Again, I can use the Fourier transform for non-periodic signals, although we're not going to do that here. We'll leave that for a signals and systems course. All right, but I do want to understand it here in this particular case. Now, what's useful about the Fourier transform, we'll see, is really when we get into some analysis stuff. All right, but when I get into basically doing some design, but what the Fourier transform allows me to do is to visualize how much energy I have at a particular frequency, which allows me to do some interesting design. So if I had an audio signal, for instance, that had an A note, so 440 hertz note, the louder that signal was, the more energy that signal has. So if I have a signal that has a small 1 kilohertz note and a really big 440 hertz note, I would know that the signal has frequencies or has energy at 440 hertz and 1 kilohertz. And if the 440 hertz signal had a bigger amplitude, there's more energy at that particular frequency than there is at the 1 kilohertz. Okay? So it sort of allows us to visualize where the energy is located. We're going to use that a little bit more and more, but this is our expression for it. And we're going to fill that out using a little bit of an example. So here's an example that we started to explore in class, which says, visualizing this guy, I see that I have what appears to be a Fourier series. All right, I have I have a DC term, 5, and then I have a cosine and a sine that are harmonically related to each other. I can tell that they're harmonically related because it looks like my cosine term has a 60 hertz frequency, and my sine term has a 180 hertz frequency. So it would appear that I have frequencies at omega equal to 0, omega equal to 2 pi 60, and omega equal to 2 pi 180. So I can identify that my fundamental here is 60, and that this guy is 3 times that fundamental. Okay, so I'll write it like so. This guy is omega naught. Okay, so I can express this in terms of a Fourier series by inspection. All right, so just looking at this, it doesn't fall nicely into one of our 3 forms. In other words, this guy is a shifted cosine, this guy is a sine. All right, so there's a couple of ways that I could express this, but I want to express it in the complex form. All right, so the n equal minus infinity to positive infinity, alpha n e to the j n omega naught t. I want to express it in that form, and I want to do it by inspection. And I can do that by remembering my Euler's identity relationships. Okay? So essentially to graph the Fourier transform of this thing, I ultimately want to get to this x of j omega equals this summation I want to do it for omega equal to minus infinity to positive infinity of a n delta of omega minus omega naught times n. Okay? That's my goal. Okay? All right. So to do that, I'm going to do that in 3 steps. So step 1 was find t or omega naught. I've already done that. That's 2 pi 60. Now I'm going to find my alpha n. And then 3, I'm going to find this x of j omega. Okay? All right, so let's go ahead and do that. So we've done step 1. So let's do step 2. All right, finding alpha n. All right, so to do that, I'm going to have to make use of my Euler's identity. Right, so I see that I've got a 4 cosine 2 pi 60t plus 60 degrees. So if I make a comparison and say, well, what happens if I said theta was equal to 2 pi 60t plus 60 degrees, and then plug that into theta, okay, that would get me something in complex exponential form. So let's say for step 2, I know that I can write x of t as, let me get this stuff out of my way because I think it's going to get close to where I'm trying to work. X of t is 5 plus, so using the Euler's identity, 4 over 2 times e to the, now because my theta is I'm going to have e to the j, in this case 2 pi 60t plus 60 degrees. All right, I can think of that as basically e to the a plus b, right? This is a, this is b. I know that that's always equal to ea, eb, like that. Okay, so I'm going to express this guy like so. 4 over 2 times e to the j 60 times e to the j 2 pi 60t plus, now I'm going to do the negative frequency term, 4 over 2 times e to the minus j 60 degrees times e to the negative j 2 pi 60t, like so. Okay? Then I have this sine term. All right, now in this case, there's my theta. This one's a little bit simpler, but I can basically use that Euler's identity, right? So a is 6, so I'll write this guy as 6 divided by 2j times, doing the positive frequency term first, e to the j 2 pi 180t minus 6 over 2j e to the minus 2 pi 180t, like so. Okay, now looking at this guy, I can do by inspection, and I can say, well, this looks like my a0 term. This looks like my alpha 1 term. This looks like my alpha minus 1 term. This guy here looks like my alpha 3 term. And this guy here looks like my alpha minus 3 term. Right? So in other words, I can write this as 5 plus alpha 1 e to the j omega naught t plus alpha minus 1 e to the negative j omega naught t plus alpha 3 e to the j 3 omega naught t plus alpha minus 3 e to the negative j 3 omega naught t. Okay, where I can write down now, alpha naught is 5. Okay, alpha alpha 1 equals 2 e to the j 60 degrees. All right, alpha minus 1 equals 2 e to the negative j 60 degrees. Alpha 3 is equal to 3 over j, and alpha negative 3 equals negative 3 over j. Now I never like these 3 over j like this. I want to get this so that I know the angle here. Alright, so the way that I think of this is I say j, I know that j is always equal to e to the j 90 degrees. And if I don't remember that, I can plug that into Euler's identity. So e to the j 90 is cosine 90 degrees plus j sine 90 degrees. Right? Cosine of 90 is 0, sine of 90 is 1. Okay? So that gives me 3 over e to the j 90, right? Which is the same as 3 e to the minus j 90 degrees if I try to write it like that. All right? Which means if I put a minus sign in front of this guy, it's going to be 3e to the j 90 degrees. Okay? Okay, so I've got now my 5 coefficients that I need to make the series. Alpha naught, alpha 1, alpha minus 1, alpha 3, and alpha minus 3. Now, let's just for sake of argument write the frequencies that these correspond to, right? This guy corresponds to DC, right? Or 0 hertz, right? Or 0 radians per second. This guy would be omega equal to omega naught. This guy would be omega equal to minus omega naught. And then these two over here, this guy would be for omega equal to 3 omega naught. And this guy would be for omega equal to minus 3 omega naught. Like that. Okay? So what we're going to do is we are going to take these expressions, okay, and I'm going to try to use those now in my step 3 here to generate that x of j omega. That's what I've done here, okay? So let's look at how I've expanded this, all right? So here I have, here's my a or my alpha 0. Right, so unpack the first term for a second. So delta of omega. So when omega is equal to 0, all right, this impulse has an area of 1. All right, so it basically says that at the frequency omega equal to 0, the energy I have there is that amplitude 5. Okay. What I see for this term right here, I say that when omega is equal to 2 pi 60. All right, so for this guy, I see that when omega equals omega naught, all right, the energy there is this 2 e to the j 60 degrees. And then at omega equal to 3 omega naught, that's what this term is, the energy is 3 over j. And then over here at this is the term for omega equal to minus 2 pi, or sorry, yeah, minus omega naught, which is minus 2 pi 60. I have an amplitude of 2 with an angle of negative 60, but this is still sort of the complex energy I could think of at that frequency. And then at omega equal to minus 3 omega naught, I have 3 over j, again, is the energy there. So how do I plot that? If I were to plot that, you can see that it's a little bit challenging because what I have is complex numbers that should be plotted on my graphs. So I really have to draw two different plots. What I do is I plot the magnitude of x of j omega and the angle of x of j omega. Okay? So let's do that plot sort of just by hand. All right, so here's x of j omega, and let's do the magnitude. Now I know that always has to be positive, and I know that there will be a value at omega naught and a value at 3 omega naught. This would be 2 omega naught, and I know that there'll be a value at negative omega naught and negative 3 omega naught. Okay, it doesn't want me to write that low in the corner there on the screen. Okay, it should be not minus 3 omega naught. All right, but let's draw in what we should. So at DC, I'm going to have an impulse with a magnitude 5. All right, so at 2 pi 60, which is omega naught, I should have an amplitude of 2. And at the third harmonic, I should have an amplitude of 3. Okay, so this is 2, 3. Now remember, those are really areas, not heights. Okay, but we sort of label the area that's there. All right, so now I'm going to do the negative half. So for the negative half, I have 2 again here, and I have 3 again here. Okay, now notice they're all positive because these are magnitudes. So now let's graph what I would have for the angle of x of j omega. Okay, I'm going to draw that a little bit higher. Now remember, this guy's a function of omega. Okay, so in this case, there is no sine at DC. There is no angle at DC. All right, so I've got nothing to worry about. Thing to remember about DC is there's really only two possibilities that I typically run into at DC, which is to say that usually I have either a positive angle or a negative angle. So if it's, in other words, it's plus or minus 5 typically. So plus a constant or minus a constant. If it's minus a constant, that means my angle is 180 degrees. Okay, so it's something we got to be careful of there. All right, so here it would appear that I got 0 degrees this time. Now, what am I going to do for omega equal to omega naught? So here's omega naught. At omega naught, I think I'm going to have an impulse here with 60 degrees. Okay, so that's 60 degrees. That's omega naught. Here's 2 omega naught. Here's 3 omega naught. Now, what's my angle at 3 omega naught? Well, we figured that out over here, right? At alpha 3, he had an angle of minus 90 degrees. That 1 over j is an angle of minus 90 degrees. So I'm going to say I've got an impulse down here to minus 90 degrees. So this is 3 omega naught. Okay. Now, let's do the negative half. So at minus omega naught, I have basically negative 60 degrees. So this is negative 60 degrees at minus omega naught. Here's minus 2 omega naught. Now at minus 3 omega naught, I have, in that case, 90 degrees. Okay, so this is 90 degrees. Now I know that because I have a 1 over j in the bottom with a minus sign out front, which we also calculated over here, gave us 90 degrees at that point. Okay, so this allows me to visualize those two elements of basically the alpha values at each particular frequency. Right? I visualize here on the left the magnitudes, and here on the right I visualize the angles. So I wrote a simple piece of MATLAB code to do that. We talked about that a little bit in class, right? So I'm basically, in this case, plotting from -7 omega naught to 7 omega naught, which means that I'm doing essentially 7 harmonics, okay? And I create an alpha vector, which is the same size as that. So then I got to figure out, well, which ones do I need to put in here? So I need to remember I need alpha 0, alpha 1, alpha -1, alpha -3, alpha 3, like that. Okay? So just to be clear now, because the way MATLAB works, right, my first index of any array is always n equal to 1. Okay? So for my n values are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, so on and so forth. Let's write what the omega value is for each of those. Well, if I look at my omega vector, the very first entry is -7 omega naught. Okay? Means the second entry, all right, is going to be, because I incremented in steps of omega naught, the second entry is going to be -6 omega naught. The third entry would be -5 omega naught. The fourth would be -4 omega naught. The fifth would be -3 omega naught. The sixth would be -2 omega naught. The seventh would be -omega naught. The eighth would be 0. The ninth would be omega naught. Right? The 10th would be 2 omega naught. And the 11th would be 3 omega naught. So what I can see is I need to enter values for, right, these were the alphas that we said over here. So I need to enter values for the 5th entry in my alpha vector, the 7th entry, the 8th entry, the 9th entry, and the 11th, right? Because those are the only 5 non-zeros, okay? So here's where I did that, right? So alpha of 5, so over here, alpha of 5, I set equal to a minus 3. Alpha of 7, I set equal to alpha of minus 1. Alpha of element 8, I set equal to alpha sub 0. The 9th entry of the alpha vector, I set equal to alpha 1. And the 11th entry of the alpha vector, I set equal to alpha sub 3, right, from before. I put those values in there, and then I make a plot. Now in this case, what I do is I use the subplot command. So the top plot, I plot the magnitude. All right, and the way I've expressed that is I put these bars in there to say magnitude. All right, and then I did the angle of x in the bottom plot. Okay, so notice here I'm using this, what I call the stem command. And that's going to allow me to make what I call a discrete plot. So it's going to only show. It's not going to try to make connections and draw a line between the different points that I'm trying to plot. What it's going to do is it's simply going to place a circle with a stem on it at each individual point. All right, each individual point in the alpha and omega vectors. So I look at what I end up getting. So I can see that at omega equal to 0, I have sort of a graph exactly like what I thought I was going to get. All right. Now notice that my x-axis here is in omega, or which has units of radians per second. All right, and it's not surprising if you look at this point right here. So this is 2 pi 60, which is about 377. So that looks like it's in about the right place. Okay, Now, what we do with this isn't necessarily abundantly clear to you at the moment, but I wanted to make the jump. I think it's not too hard to make the jump to this thing called the Fourier Transform. But this thing is useful when I want to go to design and I want to say, well, let's say I had this signal and I passed it through some sort of a filter or circuit or something. I would want to figure out what that circuit or filter is going to do to this signal. And it's really useful to be able to overlay this picture on top of what that filter's response looks like, which we'll look at later.